It's for the recording was not going.
Oh, nice. Okay. So this has been enough to scare off a lot of physicists from taking these things seriously. But there are a lot of physical theories that also have ghosts, namely gauge theories. These also have ghosts when you quantize them, but these ghosts aren't as scary because they just tell you that you have non-physical degrees of freedom in your theory. And if you restrict to gauge invariant objects, your physical states, then these are all positive. And that's as a perfectly sensible physical theory. So my goal today is to convince you that certain higher derivative theories are in fact gauge theories, and that the ghosts make perfect sense if you interpret them as coming from gauge symmetry. But we're going to do things a little bit backwards. So I'm going to instead start with a quantum theory which has ghosts. And then we're going to work backwards. I'm going to define the gauge symmetry using only the indefinite nature of the theory. I'm not going to reference any Lagrangian. And then we're going to add in dynamics afterwards and try work backwards towards a higher derivative theory that looks like this. So we start by defining a quantum theory. So a quantum theory has two parts. You have an operator algebra A, and you have a Hilbert space H. Like the simplest example of an operator algebra are your position and momentum operators, your X and P's, which satisfy the Heisenberg commutation relation. And then the Hilbert space we usually take to be square integral functions. So L squared of R. And there's two ways to construct a quantum theory. Either you first write down what H is, and then define A given H. You define A as some space of operators on H, linear operators. So these could be bounded or unbounded, but it's some space of operators on H. But you can also do the reverse. Given A, you can define H as a vector space that carries a representation of A. So you'll have some representation A or pi from A to operators on H. And in physics, we often lean towards the first one, but there are very strong mathematical reasons why you should go for the second option of this I. And that's because representations are highly non-unique. And this is really important in QFT. This is related to in curved spacetimes, you can have inequivalent vacuums. There's no preferred vacuum. And each vacuum you can think is a different representation. And so if you write down an operator algebra, there's no way to tell you which representation to use. And in quantum mechanics, this isn't as well appreciated. And that's because of the Stone-von Neumann theorem, which essentially tells you that if you have the Heisenberg algebra, the X and P's, then given some assumptions, the unique representation is the usual one, L2, where P is a differential operator. Looks like the X, and X is just multiplication by X. But if you want to look at indefinite theories, theories with ghosts, then the assumptions in Stone-von Neumann are violated, and you can have different inequivalent representations of the same algebra. So let me first.
I have a question. Sorry.
Yeah.
What does somebody mean when they say bounded and unbounded operators?
So bounded means you have some norm on H. And bounded means you can define a bound from H on your A. And so normally P is unbounded. You can see that if you look at particles on a circle, And your states look like e to the I and x, things like that. And then p is a derivative, it brings down an n, and n can be as large as you like.
Okay, I see, okay. Thanks, okay.
Okay. So let's start by defining our algebra, and then we're going to look at representations of it afterwards. Well, I'm going to define an involutive Lie algebra. This is a Lie algebra with an involution defined on it, which I'm going to call dagger. We also call this Hermitian conjugation. In more math literature, this is usually called star, but I'm going to use the physics notation. So dagger maps G to G, and it squares to 1. So if you have some x in G, x dagger equals x, the first property. The second property is that if G is complex, then it acts as complex conjugation on scalars. If you have lambda x, take the Hermitian conjugate of that, you get lambda bar x dagger. And the final property is that it swaps the order of your Lie bracket. So if you have a Lie bracket between x and y, and you take the dagger, you get the Lie bracket of y dagger, x dagger, like that. And because of these two properties, it's sometimes called an anti-involution. But so we're now going to construct an example called the block algebra F. And this, as a vector space, is a 2n plus one-dimensional complex vector space. I'm going to give an explicit basis. So this is the span of AI dagger, and essential elements, which I'll call I. And I runs from 1 through n. And then the Lie bracket on these generators is AI AJ dagger is eta ij times I, where eta ij are some structure constants that I'm not actually putting any restrictions on yet. But I want this to be an involutive Lie algebra. And so that means I need to tell you how the involution acts on the basis vectors, the generators. So I'm going to say that AI dagger, which is where we use this notation, and that the central element is Hermitian, means I dagger is I. So now if I look at dagger acting on the bracket, we get AI and J. I take the Hermitian conjugate of this, and we get A J double dagger, which is just AJ. Get an AI dagger. And this is eta JI. I can also take the dagger of this side, and I'll get eta bar IJ. Oh, this is an I there. I. And so this tells you that eta must be a Hermitian matrix for this to be an involutive Lie algebra. And because it's Hermitian, if I do a change of basis, let's say a tilde I, I'm gonna only do a change of basis that mixes. Actually, I should give these names. These are annihilation operators, and these are creation operators. So when I do a change of basis, I can mix annihilation with annihilation operators, but I can't mix the two of them. I'll make that a bit more precise in a second when I talk about vacuums. For now, let's have another basis, a tilde, which is some linear combination, the O basis, and using the involution, the a tilde dagger I is U bar IJ a dagger. And so now let's say mu ij are my structure constants to the new basis. This is the bracket of A tilde I and tilde j dagger. This is going to be mu ij and a j dagger u bar will be L j. And then using the bracket in F, this is u I k eta k l u bar L j. So as a matrix equation, this just tells you that u equals u eta u bar transpose. And under such a matrix transformation, the signature of eta is invariant. So the signature is the number of positive and negative eigenvalues. And so I can choose a basis in which eta is diagonal, and that all of the diagonal entries are either 1, -1, or 0. So eta is diagonal with +1s, -1s, and 0s like that. I'm going to assume that we don't have any 0 eigenvalues. One way to see why is I want F to be isomorphic to the usual Heisenberg algebra, the one with x's and p's. And for this to be isomorphic, eta has to be non-degenerate. So I'm going to assume I don't have any zeros here. That I only have +1s and -1s. And so I have p +1s and q -1s. So the signature of eta is pq, or p plus q equals n. And so up to changes of bases that preserve the vacuum, I have exactly n+1 different Fock algebras characterized by a signature like this. And the nice thing about Fock algebras is that it's very easy to come up with representations of them. So I want my representation to be the vector space K with an inner product which is equilinear, linear in the second argument and antilinear in the first. And I also want it to be Hermitian. That means let's swap the order. Like this. I'm not going to demand this to be positive definite. Usually in a Hilbert space, this is positive definite, which means this is greater than or equal to 0. And if this is true, then this defines a norm. And then you can take completion, and only then you can call it a Hilbert space. But because this is going to be indefinite, I don't have a norm. And so this isn't a Hilbert space. It's only a vector space with an inner product. To construct this vector space, I'm going to assume that I have a vacuum vector. Okay. And now I'm going to define the action of my operators on this vacuum vector. So the central operator, I, is going to act like an identity. The annihilation operators, I, will map the vacuum to 0. And the equation operators, A dagger, going to map the vacuum to a state which is just I dagger acting on a vacuum. And when I say state, I just mean a vector in K. And when I say operator, I just mean a generator in the algebra. So this tells you can't just have a vacuum vector in K. You also need this vector here. And now you can do you can act cyclically with the creation operators on your states and build a bigger and bigger Hilbert space, or rather represent vector space. But this is going to be an infinite dimensional vector space. So some other vector, let's say my dagger. Let's say I have a vector prime which looks like this. Then the central element is going to act like the identity. The annihilation operator here is now going to act on side. This is going to give me a dagger AI side plus the bracket of the AI AJ dagger. This bracket is just eta ij like this. And so it's easy to see then that this vector space K is spanned by vectors which look like a dagger to the end acting on the vacuum. Where this just means I have A1 to the N1, A2 dagger, the N2 up to the AN dagger, to the NN acting on the vacuum. And if you're a physicist, this should be quite a familiar idea. If you're a mathematician, you might be more comfortable with saying that K is the space of polynomials in A dagger. And then the action of the annihilation operator A is just a partial derivative with respect to A dagger I. So the annihilation operators are, you can represent them as derivatives like this.
I think you wanted to argue that the first term in that line is 0, the AJ dagger AI psi is 0.
So, yeah, it depends what this is.
Yeah.
This could be a dagger similar power beyond the vacuum.
Right, I see. But you
I
then
just wanted to say that a dagger or AX on the first operator in your polynomial like this.
Right.
And then you can kind of recursively
keep going.
all the way through. And in that case, it makes a bit more sense to think than the differential operator like
But
this.
the important thing is the only thing you ever get are the A daggers on the vacuum.
Yeah,
By applying the little A's, you never
Yeah.
get anything new.
yeah. So now I have a vector space, but I don't yet have an inner product.
Can I ask a quick question, Sam?
Yeah.
On the left side of the board there was these 3 conditions that define the vacuum.
Yeah.
So could you say again the third one, what it means that this one at the bottom? But I think I missed it.
The third one here just says that a creation operator acting on the vacuum gives you a new state, which I'm just labeling as multiplication by a dagger on the vacuum.
And so is it a third condition, or are you just saying that it?
Well, this is true for any state, not just the vacuum. But this is to motivate the idea that you can't just have a vacuum, you also need other states, or else it wouldn't be a representation of the algebra. And so that implies that the vector space is.
It has to be not 0.
Yeah. You can prove that this vector space here is unique up to isomorphism, but only as a vector space, yeah?
So normally with these kinds of things, you have like a highest weight, right? So why are you assuming that it's infinite dimensional and not that like a to the n eventually, a dagger to the n eventually annihilates something?
I mean, if you think of these as polynomials, then you can always multiply by a new A dagger.
Just
I
trying
know
to,
in more math stuff you have kind of ordering is a bit reversed. And so you'll have some, if it's a graded vector space, you'll have Vn equals 0 for n greater than some integer. And this just tells you have a vacuum, that you can't go down to infinity. You can always go up to infinity.
okay, that's,
Does that make sense?
yeah.
Okay. So now let me define an inner product on K. We've got two states. In some polynomial with coefficients alpha n, over to the n acting on the vacuum. And another state, side B, is some other polynomial with beta n, dagger to the n acting on the vacuum. And I'm going to define the inner product to be between these two vectors to be the inner product of the vacuum A dagger B vacuum like this. And I'm going to define the inner product between the vacuum and itself to be 1. And that's all you need to define an inner product. We need to show that it's Hermitian, that satisfies the properties you'd want for a space of states. So to do that, is there an eraser somewhere?
When you sum over n,
Yeah.
it's not necessarily defined, is it? Because like suppose I have a dagger plus a dagger square plus a dagger cube.
Yeah.
That is well defined.
Yeah. I mean,
Um,
this is going to be a formal series. For now, I could restrict to that being a finite linear combination if that makes more sense.
if a dagger is a creation operator for a spin half particle, and you have another a dagger which is a creation operator for spin 1 particle, you can't add them then.
Right. So I only have one type of particle here. So everything's bosonic. Then you can mix, say, A1 dagger and A2 dagger. That's fine. Yeah, I don't have any other spins. Everything's spin 0 if you want. So to prove that this is Hermitian, I'm first going to prove that the inner product state but itself is real. So this is defined as vacuum dagger A, which is going to be over n bar alpha n vacuum A and a dagger vacuum. Now I've told you how A acts on states like this, and so you'll commute it through or take derivatives through, and you'll get this object is equal to product of I and I factorial times eta I to the n I. And the important part is that this is real. On this other side, it's also going to be a delta mi. So this is 0 unless n equals n, which means this thing is real. which means the whole thing is real. Now I want to define, or now I want to prove that the inner product of the vacuum and a state is real if A is Hermitian. So this I can write as 1/2 vacuum A plus the dagger vacuum. And then I can write this as 1/4 vacuum A plus identity dagger A plus identity plus 3/4 vacuum A minus identity A minus identity. I'm not sure if I mentioned that the inner product is linear, but it is. And that's how you can write out like that. So if you multiply everything out, you'll get back to here.
You got minus sign in the second term.
Yeah. Yeah, nice. And now you see that this is something dagger times itself. So by above, this is real. This is something dagger by itself. So this is also real. And so the sum must be real.
One too many daggers in the right hand.
I do, yeah. Okay. Now finally we can prove that the inner product is Hermitian. This I'm going to do the same addition to Hermitian and anti-Hermitian. So it's going to be 1/2 vacuum A dagger E plus A dagger A vacuum, and then minus I/T vacuum A dagger B minus dagger A. And now this thing is Hermitian and it's symmetric in A and B. But this thing is Hermitian, anti-symmetric. So if I swap A and B, this term is going to stay the same. This part here is real, but here this is complex. I'm going to get a change of sign, and that's exactly the complex conjugate. Slide B, slide A, like that. So it is almost a space of states. The only thing left now is a norm and to take a completion, and then you can call it a Hilbert space. But before we do that, we need to figure out what to do with these indefinite states. The fact this indefinite is kind of clear from the equation I wrote up there, but I can make it a little bit more explicit. And the inner product of A dagger I, A dagger I equals +1 I goes from to P, and it's -1, and I goes from P plus 1 Q. These indefinite states I'm going to get rid of by defining a gauge symmetry. So let me define gauge theory. To be an abelian gauge theory as an indefinite algebra and some permission operators qi in F such that if I take G to be the subalgebra of F, which is gauge invariant, the X in F, and then e to the I T Q X between minus and T Q equals X, like this. And this thing I haven't really defined. So this thing here is defined as the formal series X plus OT eta of Q and X plus 18 squared minus 10 and so on. But, because the commutator in F gives you the central element, you know that for anything in F, that vanishes, which means all of these higher order terms must be 0. And so my gauge transformation just sends X to itself plus the commutator of Q and X. And so X is gauge invariant.
Sorry, Sam, I just, you said it and I missed it. What, F is little F as well?
Oh, that's my fuck algebra.
Oh,
With A dagger, and I. So X is in G if used with Q. Q must be with all of the generators in G, which means that Q is in the center of G. And so for a non-trivial Q to exist, meaning Q not equal to central generator, you must have a non-trivial center. So that's
Sorry, I think I missed it. Why does Q have to be the center of it's center of G? Sorry, never mind. Okay, sorry, I got
Yeah,
confused.
yeah.
Sorry.
So it's not central in F.
Okay, yeah.
It's only central in
Right.
G.
Okay, got it.
I have a question. So you have the commutator of F with F and its
Yeah.
commutator with F. So all three are F, that's why it's 0.
So the commutator of any two things in F is either 0 or gives you I. So that obviously vanishes then. I'm gonna write down a new basis for F. To make it a bit clearer, I have to get a non-trivial center in G. So I'm gonna keep the AI generators. I went from 1 to 2 minus Q. And then I'm gonna define a generator BI, which is a P minus Q plus I times A P plus I, for I running from 1 to Q. And then I'm going to define a B bar, to be the same thing, but with the sign flipped. Minus a plus I, and for the same i's. And then the respective creation operators are just defined by taking the Hermitian conjugate of these things. And the important thing here is that EI, EJ dagger equals 0. And similarly for the bars. It's because you've one positive generator and one negative generator. And so the two things cancel when you commute that bracket. And the same is true for the bars. But the B's and the B bars don't commute. So B I EJ bar dagger is equal to 2. You're going to get a sum, or you're going to get a positive 1 minus a negative 1. So you're going to get 2I delta EJ. Right, so I'm going to take G to be the algebra spanned by the A's and the B's, but not the B bars. And then I'm going to say that Q is going to be in the space spanned by the B's. I'm going to say Q. Actually, I might I'll leave it general for now. So Q is going to be some Hermitian linear combination of the B generators. So it's going to be ZI, BI, plus Z bar I. And then just the Q dagger equals Q. And now if you look at into the IQ or ITQ and something in G. So if X only contains A's, then they commute with the B's. I dagger equals 0, and same for the bars. And so Q commutes with the A's, it commutes with the B's. The only thing it doesn't commute with are the B bars. And so X is only gauge invariant if it's equals X, if it's in G. Another way to think of G is that this subalgebra is ideal in F. Take a bracket with G and F. I either get 0 or I get the central elements, and that is contained in G. So that means I can look at a quotient F, quotient G, we call it G0. And I want U0 to admit a section such that it looks like an abelian subalgebra of F. So this, let me say it's isomorphic to an abelian subalgebra of F. And now you can start counting dimensions. So for G to be abelian, B0 to be abelian, let's have dimension less than or equal to Q. And for G to be positive, it has to have dimension less than or equal to E. But this plus this has to equal this. So that means the dimension of this has to equal Q. The dimension of my physical algebra has to equal P. And so I'm forced to include all of the B's in G and none of the B bars. So this, I can think of G0 like this.
And could you so maybe just summarize the logic one more time? So you're saying, did I understand correctly that you're gonna start with a Fock algebra little f, and then you're gonna sort of the idea that you are thinking that you sort of choose some operator, sub-operators Q, and then define little g to be the subalgebra that is
Yeah,
Can you split all of those?
so another way. Actually, let me redo this a slightly different way, so it might make it a little bit easier to understand.
I'm asking because I didn't, and one way to do it would, one, I think is. Because they didn't follow the last step, how did we know that P0 was gonna be a building?
I am requiring it to be abelian. And the reason I do that is to figure out what the dimensions need to be. Let me, say it a different way. The negative generators, the AIs for I greater than P. The AIs. Of the commutator with the wrong sign. I don't want those to be physical. So I want this commutator to be non-zero for I greater than P. And so that means my Q has to contain an AI dagger somewhere. So Q must be AI dagger plus something. But I want Q itself to be null. I want Q. The way I think of it. This is permission.
Well, I'm a little worried I'm throwing off this course of this story, which was going very. I didn't mean to disrupt the overall flow. But,
okay. But the point is that Q is going to be some null combination of the positive and the negative ones. So it's going to be like if this is a -1, I have some alpha here. This is going to be a +1 plus the mission conjugate of it. Then I need magnitude of alpha to equal the magnitude of beta. Because otherwise I could have Q acting on the vacuum and get a negative state out of it. That's why I chose Q to be some linear combination of the B's, because the B's themselves are null combinations of positive and negative. Does that make it a bit clearer? Okay.
I have a question, sorry.
Yeah.
Are the B's in the linearly independent set there?
Yeah.
Somehow you have you've taken complex combinations of A's and you have equally many. You have I still running from 1 to Q, right? So don't you have?
No.
Have you?
So what I've essentially done is I've paired up one positive direction with one null direction or one negative direction, and then chosen light cone coordinates.
Okay, I see. Okay.
This was like the +1 and a -1. I've chosen my B's to be B bar like that.
Okay. Right. Okay. I see. Okay.
And that's just a choice I made. I mean, you could always do a change of basis to make it look like this.
Right. Okay. I see. Okay. All right. Okay.
Yeah. Now, if I look at everything in G, the commutator of, well, the B's are obviously null, and the A's are positive, which means if I construct a representation KG, which is constructed in the same way as the last one, but now I only look at creation of this of AI dagger, where the I's run from 1 to Q, and VI dagger, let me say acting some power, or the B, I guess acting on the vacuum. So my vectors now look like either positive creation operator vacuum or null ones. And so this is a positive semi-definite space. So any vector in K, the inner product that I defined earlier is going to be greater than or equal to 0. Well, it is a degenerate product because or inner product. B daggers. The B daggers are known. And so they're orthogonal to everything else. So if I say A0, all of the vectors the inner product with themselves is 0. We define H as the quotient of K0 like this. Now this H is positive definite. The inner product is non-degenerate. And so it defines a norm on H. And in here I can now find an inner product. And take a completion, and H is going to be a Hilbert space. So that's how you get your, we call this the physical Hilbert space. And so that's how you start off with an indefinite one, and you get a positive one through gauge symmetry. We have about 10 minutes left, right? Okay. Let me say a few things about dynamics, because I promised you a higher derivative theory. Oh, another thing to mention is that this selecting the gauge invariant subtheory, this is usually called Gupta-Bloiler. So in Maxwell theory, you have 3 positive directions, which are your space-like photon polarizations, and you've one null, which is your time-like, and then you normally combine one of the positives. Yeah, so you normally combine one negative, one positive to get a null, and then you're left with P minus Q, which is 2 photon polarizations. But the nice thing about this is that you can do it all in quantum mechanics. You don't have to go into the field theory to see it. So let me add in some numbers. I want a Hamiltonian H, which I'm going to say is Uij, A dagger I, A, J, where these are now in F. These could be negative ones. And then I'm going to define time translation as x going to e to the I t h x e to the minus I t h. And for this time translation to be compatible with this gauge theory structure, I want e to the I t of G of my physical subalgebra. I want this to be contained within G. So if I start off with a physical operator, I don't want to time translate into a non-physical one. And so let me make things simpler, say P equals Q equals 1. This is the simplest possible gauge theory you can have. And so in G, I have two generators, BI, which I'm going to set, or B, should I even do a name? B will be equal to A1 plus I A2 B dagger, which is A dagger minus I A2 dagger B dagger equals 0. And I have no positive generators in G because P equals Q equals 1. There is no AIs, and so my Hilbert space is actually trivial. So I start off with a vacuum vector, I act on it with B dagger, and I get something null. So that disappears when I take the quotient here. So H, in this case, H is just C times the vacuum vector. It's one dimensional, well, one complex dimension. So now I want this Hamiltonian here. Actually, I'm going to make a further assumption. I'm going to say that H B dagger is equal to omega B dagger for some real omega. And this guarantees that when I do time translation, I stay within G. And we get back to my A's or my A daggers that I had before. So, in the interest of time, I won't do the calculation, but I will claim that if you impose this condition on H, then the most general Hamiltonian you get looks like omega times A1 dagger minus A2 dagger A2 plus lambda times B dagger B. If you look at e to the I T H B dagger equal minus I T H, this gives you e to the I omega T B dagger. So time translation just acts as a phase. But if you look at a non-physical operator, so something that's not in G but in F, and do time translation, e to the I T H, it's like A1 dagger e to the minus I T H, you will get the I omega T one dagger plus I dagger. And now you'll see that this time translated operator satisfies the harmonic oscillator equation. If I call this thing E dagger, then EDT squared plus omega squared B dagger of T equals 0. But this operator equals A1 T. This does not satisfy the harmonic oscillator equation. This instead satisfies EDT squared plus omega squared A1 T. This satisfies a higher derivative equation. And you can show that this, so you can think of the space of linear operators, your A's and A daggers, as being your classical theory. And so this tells you that your classical variables satisfy a second order equation. And so it turns out that as a classical theory, this looks like the action is an integral dt. It's squared x squared. And this gauge symmetry, sends x to x plus y, where y satisfies the harmonic oscillator equation. So this looks very similar to Maxwell theory, where you have something like dA squared, and you can send A to A plus dF, where F satisfies the square root of your differential operator. Like, and then d squared f is 0. And so it looks exactly like the abelian gauge symmetry in Maxwell theory. And so I guess the conclusion is that certain higher derivative theories, in particular one where the Lagrangian looking squared, these have abelian gauge symmetry, the exact same way the Maxwell theory does. When you treat that a serious gauge symmetry, you select your gauge invariant objects, you quotient out by all the null things, you get a perfectly positive physical theory at the end of it. Now it is a completely trivial theory. It's still above H is one-dimensional. And so as a quantum theory, it's not particularly interesting on its own. But it is a perfectly sensible physical theory. And I guess that's why you shouldn't be afraid of certain ghosts.
I'm for a couple of questions. Anyone wants some final questions?
So you have your Fock space, and like some part of it also acts as the generator of the gauge group, which is abelian.
Yeah.
So the action will always be adjoint.
Meaning a commutator. Yeah.
This is because you're working just with the algebra of operators and not on representations.
Yeah, so you could, I mean, I did lie a little bit when I said my algebra was just a Lie algebra. And you could instead work with the universal enveloping algebra. And there your Q will be a polynomial in the B's and not just B plus B dagger. But it's still true that the commutator of Q is something with a physical thing will vanish. And for non-physical things, you'll just get something proportional to I. So you never get non-abelian gauge symmetry out of this.
Like, just a follow-up question. So is it fair to say that if you have a theory which has ghosts and higher order derivatives, we don't really need to worry about the negative norm state, because you can take a linear superposition of those states to get something which looks like a gauge symmetry, and there are no negative norm states.
Yeah, but that's only given this condition here. So you can write down an action which looks like double that plus omega 1 squared of x double that plus omega 2 squared x. So it's two harmonic oscillators but with different frequencies. And that Hamiltonian doesn't satisfy this property. If you start off with a physical operator, you'll get outside of G in the time translation. So it's not that all higher derivative theories make sense. Only certain ones that do. And the ones that do are the ones that behave well under time translation. And you can kind of see that this Lagrangian doesn't equal something squared because you have two different frequencies there.
So Philip Mannheim was claiming this does make sense.
Yeah, I think I'd disagree though.
If you use a different inner product. Then he has to use this PT.
I asked him about it. He was working in these L2 spaces, and his inner product, well, he assumed a Hilbert space. These kind of projection operators to get wave functions. So he assumed a positive Hilbert space and then found a contradiction, which I think you can interpret that as saying your inner product's wrong, or that you haven't dealt with the negative norm stuff correctly. So I don't particularly like his inner product. It seems a little bit artificial to me.
I don't know if there are any physical operators in that theory, which is in
Right. I haven't looked at his stuff with operators. This is very.
when you use these PT symmetric quantum mechanics, that one of the problems is that the operator you start off with, like X, doesn't turn out to be real. It's not observable, so it's quite tricky what is or isn't observable. But with your operator, X didn't end up being observable either, right? Because it's not gauge invariant.
Yeah.
So yeah, there's trickiness on both sides.
Yeah. I think I need to work through his stuff and what you about to really say more.
Can I ask?
Yeah.
Very stupid question, probably. You think that all of this that you showed would change if you work with quantum field theory instead of quantum mechanics? And if so, how?
So in the QFTs we've looked at, we haven't done it in this order. We've started with the Lagrangian, assume the gauge symmetry. Then you know what Q is from the Lagrangian. You don't just guess it based on the indefinite structure.
Okay.
I mean, you could possibly do this in field theory if you pick a time slice and then your A's and your A daggers live on that time slice. And you could, I think it would work out the same. But usually we go the other way where you have Lagrange, you know what Q is. So you know what your gauge symmetry looks like from the start.
Okay.
So let me ask a philosophical question. Gauge symmetry is appealing because it's very geometrical and related to fiber bundles and so on. What's going to replace it in this picture? This is nice. This is appealing because it's entirely quantum. There's no classical picture. But what are we going to replace the classical geometry with?
I don't think I have a good answer to it.
We're just going to become algebraic. Forget about geometry and just do algebra.
That was that Atia's deal with the devil, isn't it?
Yes, exactly. Atia says that's what was it? It's the compact with the devil. Algebra is much more powerful.
You'll be able to answer anything you want with, but you have to give up geometry.
Right.
Yeah, I mean, there isn't a local gauge symmetry here that you're fixing.
Right.
So all of these are kind of residual gauge symmetries. So it's Maxwell theory after you've gauge fixed.
Right.
There's no, you probably want that initial local gauge symmetry to start talking about.
I see.
Well, in a sense, you construct geometry, no?
Maybe, is there any questions from online?
Yes,
Just
there
a
is
quick
one.
comment also, there is a recent paper on the interacting version of this kind of theory.
Right, yeah.
Which does introduce interaction, but it also has this kind of gauge symmetry, so that looks like a.
Does he do BRST in that paper?
He doesn't, but he should. He doesn't know how it's related to BRST.
Costas, did you have a question?
Yeah, it's not exactly a question, more like a comment. So, hey, can you hear me? Can you hear me?
Okay, this is our problem.
Oh, yeah, it would make sense because the is mute. Okay, try again.
Can you hear me?
Yes, there we go.
Okay, perfect. Well, it's not exactly a question, more like a comment. What Sam's work is doing, he's basically choosing a geometry by choosing the correct scalar product. So I don't know whether you really exchange algebra with geometry. It's just that it seems we're in some early stages where we have to figure out the algebra in order to figure out the geometry. At least that's the way it looks to me.
How do you see the geometry in this algebra?
From the inner product, essentially. Okay. You choose an inner product and therefore you have a geometry.
It's not picking a connection, it's two different things.
But I guess that's very different than the geometry of space-time, at least as it looks at the moment. Or, well, or is it? I don't know. Yeah, at least I didn't, then the eta that appeared in the Costas, does the eta that appears in the algebra for the A's relate in some natural way to the geometry of space-time, or are they two different geometries?
You able to hear that, Costas?
Yeah, I think so. Most of it.
It was from far away. Maybe I can repeat it. He's just saying, does the eta that appears in the commutation relations have anything to do with the geometry related to the inner product?
Well, I should hope so, but maybe you should ask Sam and not me for that.
Can I have a question?
Yeah.
So when moving from quantum mechanics to QFT, there might also be the issue that when you introduce an infinite amount of these harmonic oscillators, these annihilation and creation operators, you then, first of all, the vacuum state is not guaranteed. You have to postulate it, right? And then you might also construct so-called strange representations which are inequivalent. So the vacuum state of one representation that does not have to be found in the other representation at all. Do you think you might run into these kinds of problems when moving with this picture from quantum mechanics to quantum field theory?
If we try to do it the way I did today, then yes. But like you have to drop positivity of the inner products. Like even if you keep positivity, you've infinitely many different representations. So this makes it even worse in that sense. So yeah, no, I think we will have those problems.
Okay, well, maybe let's thank Sam again, and if there are further questions, we can take them to the pub. You can go. Good, yeah.
I don't use that for notation.